This is lab presentation 1 by Lana and Destiny, track B. In this experiment, we determined the charge of a piece of tape to be 76 nanocoulombs using Newton's second law and Coulomb's law. Then we calculated the percentage of atoms that had given up their electrons. Before we start this experiment, we first estimated our upper and lower bounds of the possible charge on the tape and the number of electrons on the piece of tape. To find the number of atoms, divide your length and then your width by 2 angstroms. Then multiply the number of atoms along the length by the number of atoms along the width. You can see here we have our length on top divided by 2 angstroms multiplied by our width divided by 2 angstroms. Some of the assumptions that we made for our experiment. Number 1. The charge on both pieces of tape are the same. 2. The charge is concentrated at the center of the tape. But tape is an insulator, so the charge is spread uniformly over the strip. Gravity is also approximated to be 9.8 meters per second. For the experiment, prepare charged tape and hang them on stable supports. Make sure that the supports are insulated so that they do not strip the charge from the tape. Also, be careful that the tape does not touch your hand because it will lose its charge. It is attracted to your hand as it polarizes your sweat. We know that the tapes are repelling each other because they are both negative. We discovered this by charging a balloon by rubbing it on our hair, then watching the tape repel. Using a tracking software allowed us to find the length of the tape and the angle that we will use to determine the charge. We were also able to find the distance between the two supporting rods, which we will discuss in the next slides. Right here, R is equal to D, which is D right here, plus 2 times 1/2 L sine theta. This is because these both tape A and B both make the same angle. 1/2 L is the hypotenuse, and we'll be able to find this length by using sine. Here, the force applied in the x direction is equal to Fa sine theta. That is this right here. Fa in the x direction is equal to Fa sine theta. Then the force applied in the y direction is equal to Fa cosine theta in the y direction. So we know that Fe is the same, is equal to Fa sine theta. That's Fe right here. In the x direction. And in the y direction, we have the force weight right here is equal to Fa cosine theta. Since both of these equations are true, we can divide them by each other. And we get Fe over force weight, which our Fe equation is K Q squared R squared. And we know that force weight is mg. And if we divide sine theta by cosine theta, we get tangent. Now we solve this equation here for Q, and this is what we get, with this being our R that we solved in the previous slide. These are what we found using tracker, D, L, sine theta, and mg, which we found by using the length multiplied by the density. K is our constant, and Q is what we gathered from plugging it all into our equation. Next, we calculated the fraction of atoms to give up or accepted electrons. Here explains the math, in that we got 0.000375% of atoms had given up their electrons. In summary, the charge of the tape was determined to be negatively charged because it was repelled by a charged balloon. 2. 0.000375% of atoms gave up their electrons, and the magnitude of the charge of the tape was 76 nanocoulombs.